Okay, so as we saw in class today, right, um, we can draw or we can graph many different types of graphs if we know the base function. Okay, so what we're going to learn about today is not the base functions in general, but just the transformation rules. Okay, so there's a lot of ones to think about. The two biggest things we want to consider when we talk about transformation rules is this idea of doing something outside the function versus inside the function, okay? So let's take a look at some outside the function transformations first. So f of x plus d, that means we're doing some type of addition outside the function. Okay, so we perform some operation, we have some function, and at the very end we add something to the end. Okay, the visual effect of this is that the graph, okay, is going to shift up by d. Whatever d is going to shift up by d. Okay, what does that mean for the points x and y? It just means it moves y up by whatever d is. There should be a space there, but it moves y up by d. So if you have this point xy, your new point after it's been shifted is going to be x doesn't change, comma y plus d. So whatever d is, we're just going to add to it. So let's just take, for example, we have this function f of x plus 3, and let's say we have this point 3, 4 that's on f of x. Well, if I add 3, if I have the function f of x plus 3, how does it differ than the function f of x? Well, that point 3, 4 that was on f of x will become, what do you think it's going to be if we add 3, comma 7? Okay, so addition outside the function means we move up 3, or move up d, in this case it was 3. If it's f of x minus d, you can guess it's going to shift down d. Okay, it's going to shift down by d. In terms of the point, okay, it moves y down d, and the point x comma y becomes x comma y minus d. So for example, if we have a function f of x and we're comparing to the function f of x minus 3, and again the point 3, 4 is on f of x, what would the new point be? Well, it would be 4 minus 3, or 3 comma 1 would be our new point. C f of x, c just represents a constant. Okay, it means we're multiplying the function by some constant on the outside. Okay, so c times f of x, what effect does that have on the graph? Well, visually, it dilates by c. Dilates means like shrink or enlarge. So your graph's going to become either bigger or smaller by this c amount. Okay, so what it happens by with the points, it dilates y by c. So in terms of our points, x doesn't change at all, but what happens is we're going to multiply, okay, we're going to multiply the y value by c. So it's going to be c comma y in this case. Whatever the y is, we're going to multiply it by c. So for example, if we have something like 2 f of x, what happens to the point 3, 4? Well, it becomes 3 comma 8. We're multiplying all the y values by c. And then the last one, negative f of x. Okay, the effect that will have is reflect over the x-axis, running out of room. It's going to reflect over the x-axis. Point effect, it's the same thing. It's going to reflect over x-axis. What does that mean in terms of your point? Well, if you think about it, if it reflects over the x-axis, and I have a point up here, let's call this point 3, 4, and you reflect it over the x-axis, that means it's down here. The x doesn't change, but the y is just going to change. So in terms of the coordinate xy, instead of xy, we're going to have x comma negative y. So for example, if we have the function negative f of x, okay, what's going to happen to my point 3, 4? Well, as we saw above, 3, 4 is going to become 3, negative 4. Okay, so those are all examples of shifts occurring outside the function. When we start looking at specific examples or specific functions, I'll go into more detail as to what we consider outside the function versus what we consider inside. For right now, I just want you to understand the rules that go along with this. That if we have something outside the function that we're adding, it shifts up. If it's we're subtracting, it shifts down, and so on. Okay. The other big thing I talked about was inside the function. Inside the function means that we're performing some transformation before we do what the function intended us to do. Okay. So for example, if I have f of x plus d, and I'm adding d to x before I do anything else, okay, what effect is that going to have? You might think it's going to shift right, but it's actually going to shift left by d. It's going to shift left d. We'll go into more detail on that on our next class, but for right now it's going to shift left d. It moves x left by d. Moves x left by d. So what happens to the point xy? Well, if we want to move it left, we actually have to subtract it, subtract numbers. So it's going to be x minus d comma y. So for example, if I have the function f of x plus 3, okay, and I subtract 3 from the x value, 3 minus 3 is 0, so my new point becomes 0, 4. F of x minus d, it's going to shift right by d. It's going to shift right. Point effect, what does that mean? It moves x to the right by d. And in terms of our point, x plus d, comma y. Notice only the x changes in this case. It's a little bit counterintuitive. You'd think if we're adding something on the inside the point, we're going to add something to the point. It's reverse when it's inside the function. So if I have something like f of x minus 3, I'm going to add 3 to the point. It's going to have the opposite effect. So adding 3 to the x coordinate is going to become 6 comma 4. F of cx, that means we have a dilation on the inside. Okay, it's a little bit tricky. We're not going to see a lot of these, but I do want you to be familiar with it. It's going to dilate the graph by c, just like c f of x did up here. Okay, but notice the c is now inside the parentheses. It's considered inside the function. So instead of dilating y, it's going to affect the x value. So it dilates x by c, meaning what's going to happen to my point? It's actually going to be divided. It's going to be x over c, comma y in this case. Okay, x over c. I'll go into more detail again on that our next class, but for now, just remember it's x over c, comma y. We're going to divide. It's kind of counterintuitive again. So f of 3x. Okay, what's going to happen to 3 comma 4? Well, if we divide 3 by 3, my new point's going to be 1 comma 4. And then the last one, f of negative x. If there's a negative on the inside, what's that going to do instead of reflecting over the x? It's going to reflect over the y-axis. In terms of the point effect, what happens to the point? It's the same thing. Reflect over y-axis, meaning the x value will change this time. So instead of x comma y, it's going to be negative x comma y. Okay. For example, if I had the function f of negative x and the point 3, 4 was on f of x, I'm going to have to flip the sign on that x coordinate. So 3, 4 becomes negative 3, 4. We'll talk a little bit more about the intuitiveness behind this in the next class, but for right now I want you to be familiar, okay, with just the process of this. Because if you're familiar with the process, it makes graphing all the other functions we see much, much easier. Okay. Now if you notice, one thing I want to point out, the last row in each table are reflections. When it was outside the function, right, when it was outside the function, outside the function, right, up here, f of x, it reflected over the x-axis, and when it was inside the function, it reflected over the y-axis. It's easy to get them confused, so I want to show you a little bit of a device here that may help you remember. So if my negative is on the outside, okay, if it's on the outside, I say it's like, imagine you're outside and you're looking at your reflection. If you're outside looking at your reflection, one way you could do this is you're looking, okay, it's like you're looking at a reflection in a lake, right? So again, we think outside, negative f of x, it's outside the function. Where are you going to see your reflection outside in real life? It's going to be, okay, it's going to be in a lake. Okay, so if you think about this, there I am. Okay, let's draw some water here. Okay. There's our water. Okay, imagine looking at your reflection. Your reflection is going to be up and down, right? Your reflection is going to be up and down if you're looking, okay, at your reflection in the lake. So think of that as kind of like your x-axis, right? If you're looking up and down, okay, if you're outside, you're looking in a lake, your reflection is going to reflect, okay, over that lake. Think of that lake as kind of like the x-axis. If you're inside, what's a common thing you look at inside to see your reflection? Okay, it's like a mirror, right? Like a mirror. So if you're standing here, right, and you've got a mirror on the wall, okay, okay, your reflection is a vertical reflection, right? Okay, it's like you're reflecting over the y-axis in this case. That's if it's inside. It may help you, it may not. Some kids like it, some don't. But if it's outside the function, it's like you're outside looking at a lake. It's up and down, your reflection's up and down. If you're inside, right, if you're inside, you're seeing your reflection in a mirror. That's a vertical reflection, right? Think of that as like the y-axis. If it helps, great. If it doesn't, don't worry about it. It's something that some students have liked. Just a couple things, or one last thing here in terms of this. When we think about multiple transformations, okay, there's a rule called HRDV. Okay, HRDV is like the order of operations of transformations, right? H stands for, we're going to do any horizontal shifts. That's what our H stands for. What do you think R stands for? We're then going to do reflections next. D, dilations. And then V, vertical shifts. So if you encounter multiple, okay, transformations in one function, you're going to do horizontal shifts first, reflection second, dilations third, and vertical shifts last. Okay, those are the order operations in which to complete all of these. So let's look at a couple, and then I'm going to let you try some on your own. So let's take a look at this function we have here. It says, given the graph of f of x shown to the right, sketch a graph of each of the following. And what I'm actually going to do is actually redraw the given function here real quick, so you can kind of see the transformations in action. So I'm just drawing a few of the points. So again, here is my original function. I'm using a dotted line to show you that it's the original function. I'm going to do the actual function in blue. So if that's f of x, what would f of x plus 2 on the inside minus 3 look like? Well, let's think about our HRDV rules. HRDV would say you'd have to shift everything to the left, or shift everything on the inside first, and then take care of that minus 3 on the outside. So remember, when we do plus 2, that means we're shifting to the left, not right. So what we're going to do is take each one of these points, and we're going to shift every point to the right 2. So my new temporary graph would look something like that. That would be f of x plus 2. But we also have a minus 3. So my graph is not complete yet. Now I'm going to take those points, those ones in blue, and now shift those down 3. So this point here at the bottom moves down there, that moves there, that moves there, that moves there, and your new f of x plus 2 minus 3 is that function in green. That function in green would be my final answer. So you can see from that black dotted line to the blue dotted line, the steps you would want to take in this. And refer to that table. Use that table to help you. Okay, the table will be very, very helpful in doing this. I don't expect you to have this memorized in 20 minutes. But I do expect you to be able to take that information on the table and transform it to these graphs. Let's maybe do one more together. Let's try B. Let's try B. So if it's helpful to you and if you can do it neatly, you can redraw the original function, especially early on. I find it very helpful. And I would always do it in a dotted line to make it clear that that's not your answer, right? It's just where the original function is. So again, this is 2 steps. So if you think about the order of operations, we have a negative on the inside and a plus 3 on the outside. Again, if I'm thinking of my HRDV rules, HRDV, do I have any horizontal shifts first to do? I do not. Do I have any reflections? Ooh, yes I do. I have a negative on the inside. And it's on the inside. Is that the x or y axis? Again, let's think about if you're looking at your reflection on the inside, that means you're reflecting over the y axis. You're looking at a mirror. That's a vertical type of reflection, so over the y axis. So let's just take all these points and reflect them over the y-axis. So the point negative 2, 0 becomes 2, 0. Okay, negative 1, 3 becomes 1, 3. So notice how these points look like they're the same, but really the point on the left shifted to the right or reflected to the right, and the point on the right reflected to the left. And then I'm taking this point 1, 2, and it's becoming 2, 1 becomes a negative 2, 1. So the graph has just really just kind of been reflected over the y-axis. But again, that's not my final graph. That's just the reflection part. Now I need to move all the points up 3. So if you count 3 up from all the graphs, or from all the points, we get a graph that looks like that. And that graph in green would be my final answer. So just be very careful. Go slow. There's no rush. We already did 2 of them together. There's 2 more for you to try to do. Remember to keep straight the inside shifts. Remember, it's always the opposite. So refer to the chart when doing those. And I just want to do one example from the last page. It says describe the transformation from the dotted function f of x to the solid function using function notation. Okay, so basically we're doing the reverse. Here I'm giving you the transformations and I want you to write what the equation would be in terms of f of x. So again, if we look at this function here, the dotted one, that's our, right here, that's our f of x. That's what we start with. And notice that after we've done our transformation, this is our new f of x. So what would you have to do to f of x to get that new f of x graph? Well, you would have to add 2. Notice how all the points move up 2. You have to add up 2. Let's just do one more together. Let's take a look at this next one. We have this dotted function. Again, this is your f of x. And it looks to me like all the points have just been shifted left 3. So it's been shifted left 3. So what do I need to do to the function to shift it left 3? Well, we do know it's something on the inside of the function, or at least I hope you know it's something on the inside of the function. So it'd be f of x, and if I wanted to shift left 3, I would think you'd want to add, but it's actually the reverse, right? So we're actually going to shift this, and we're going to shift it, sorry, you think you're going to subtract 3, it's going to be adding 3, so we're going to do f of x plus 3, okay? Some of these get a little bit harder. Some of them have multiple transformations in one, okay? This one could be a little bit tricky. Okay, this one could be a little bit tricky. They really all could, to be honest with you, but do your best. Try to identify what those shifts are, and remember that you must adhere to HRDV. Okay, adhere to HRDV. Think about what you would have to do first. Are there horizontal shifts left to right first? Are there reflections first? And try to go about it that way. We'll talk more about this in our next class, but hopefully this will give you a good start to try to finish this.